All right, in the first video we talked about large and small scales. Now I want to talk a little bit more about scale on maps. So first of all, let's define this word that we've been throwing around. We use scale an awful lot in our language, and one of the things that is probably confusing about the stuff we talked about in the first video is when we talk about something being large scale, we often think about it being a large thing, but with maps it works a little differently. So what are we actually talking about with scale on maps? In a wordy version, we're talking about the relationship between the map distance and the same space on Earth, or the ground distance, right? So a way that we could sort of shortcut this is to write map over ground. So the relationship between the distance on the map and the distance on the ground. Yeah? So if something is an inch long on the map and it's a mile long on the ground, that relationship is 1 inch to 1 mile. And there's a lot of different ways that we can express this. Well, I say a lot. There's three basic ways that we tend to express this on maps. And the first one is that verbal scale. So the 1 inch to 1 mile that I just referenced. This is a good way to convey distance quickly, with a distance that you expect people might be familiar with, right? So if I say 1 inch to 1 mile, you should have a pretty good idea how big an inch is, right? It's our wacky system that hardly anybody else in the world uses anymore, but if you grew up with that system, you should have a pretty comfortable idea of the distance. If you grew up with the metric system, you're going to have probably something like a centimeter much more familiar to you. And then a mile, maybe picture something in your head that you know is roughly a mile. Or if you think about a typical track, like in the Redwood Bowl, right? That's usually a 1/4 mile track, so 4 times around that track gets you a mile, and you can kind of think about that. So verbal scales use big round numbers, right? So we're not going to say 2.7 inches equals 10.1 miles, because that's awkward, right? People aren't going to be picturing that in their head. We're going to round it up, and we're going to say 3 inches equals 10 miles. Round it up or round it down, depending on what's happening. And so this has a purpose, but it's not super good for maps that we're going to reproduce, right? If I blow this map up or I shrink this map down, that scale is no longer valid, for one thing. And it's also, remember, because we've rounded it, it's not highly accurate. Or precise, for that matter. Either way. It's accurate enough for the task at hand, but it's not very precise, and it's not going to be accurate for doing fine measurement, okay? So you might find this on something like a touristy map, where we're trying to kind of quickly tell you, hey, this walking tour is going to take you, about this long, right? Because this size of the map is maybe a half a mile. The next type that you'll see sometimes is the representative fraction, and it's typically written, even though we call it representative fraction, and we're going to write it as fraction a little bit when we work in things, typically when it's on the map, it's written in this ratio style of 1: whatever. And this is that same map to ground ratio. So in this case, it's map on the left, ground distance on the right. But there's a trick here, right? So the map distance and the ground distance in the representative fraction have to be in the same units. And the reason we do that is so that we can take the units away, and then we can add any units we want. So, your book uses Oreos as an example. In this particular case, 1 Oreo equals 211,200 Oreos in the real world. You could use pink elephants, whatever you want to use, doesn't matter. 1 whatever is the same as 211,200 whatevers in the real world. Okay? So, you could use the width of your thumb. I mean, I wouldn't want to probably lay my thumb down 211,000 times to get where I'm going, but it gets you there, right? So here's an example. 1 to 3,168,000 is the same as 1 inch equals 50 miles, right? So in a verbal scale, we'd say 1 inch equals 50 miles, but in a representative fraction, we do this. This is still awkward. This still changes if we zoom in or out of the map, if we blow it up or shrink it down. So it's still not perfect, but this gets used a lot when we're producing a series of maps at the same scale. So for example, the topo maps that you're going to be working with, you're working with the 1 to 24,000 series. So all of the maps produced in that series we know are at the same scale, and we could patchwork them together. You could wallpaper your house if you want. And we know they're all the same scale. So you can move from one map to the other without changing scale, and it's super useful. So that's the main reason that we use the representative fraction, is to be able to do that, to make sure that we've produced a series of maps at the same scale. There might also be some particular reason to produce maps at a specific scale. There's an extra credit lab that you guys have available to you this term that's designing a base map, and you're asked to produce it at a particular scale. But like I said, most of the time you're going to find this on something like a topographic map or a map series. We have a giant map we used to lay on the floor during Geography Week, which is in November, that is a 1 to 500,000. Every map in that series is 1 to 500,000, so we can lay them out, tile them out on the floor, and make a gigantic continuous map, which is really great. However, the one that we're most often going to use when we make our maps in GIS is this one, and it's a bar scale or a graphical scale or a scale bar. It gets a couple of different names, but it's all basically the same idea. And what happens here is because you have drawn on the map the ratio, that relationship between map units and ground units, as you shrink or enlarge the map, the scale bar shrinks or enlarges. And so it works no matter what happens to that printed map or static image or whatever, right? If you're zooming in and out on Google, you'll notice your scale bar changes with you. That's a different animal. I'm talking about a static map that we shrink down or we blow up in order to see it better. And the scale bar travels with it, and so this is really the most practical scale bar to put on a map, or the scale type to put on a map is the scale bar. Okay? So, what do we do with it once it's on there? Well, the easiest way to measure, and the way that we often have you do this for the first lab, and you'll probably do this in your scale lab as well, just on your own instead of in a group, is you take a little piece of paper and you put a tick mark at thing A, and you put a tick mark at thing B, and then to figure out the distance between thing A and thing B, you're going to hold it up to the scale bar. Now the trick is to pay attention to this, right? The scale bar doesn't always start at 0, particularly on topo maps. Oftentimes 0 is somewhere in the middle. And the reason they do that is so that on this side you can have big units, like in this case it's 1,000 meters, and then on this side you can have small units so that this doesn't get all cluttered up, right? And so what you're actually doing is you're taking 1,000 meters and then you're adding to it 500, and here they say it's 20. I can't really tell from this picture, but we'll take their word for it, right? So it's not 1,000 meters here, it's 1,000 plus 500 and whatever, 520. All right, so be very careful when you take your piece of paper to the scale bar that you do that. The other way you could do it is you could put A at 0, right? And then when you get to 1,000, you could just put an extra tick mark here and then reset so that that tick mark to B goes this way and you get your 520, and then you add the two together. Okay, so there's a couple different ways to do it, but just pay very careful attention to where the 0 is when you do that. All right, so that works super great if the two things are in a straight line from each other. But we know that geography doesn't often cooperate with us in that sort of way. So what happens when it's bendy? Well, you can use a piece of string or something that's bendy, right? And then I would put a mark on the string in both locations. Straighten the string out, lay it against the scale bar, and I'm good to go. When I took the version of this class that I took back, shortly after the crust of the earth cooled, my lab partner and I were advised to bring some string for our lab to do this, and he said, "I'm on it, I've got it," and he showed up with minty dental floss. So every time I think about this type of measuring, I think about minty fresh dental floss. And it was a sort of a running joke with the two of us through the entire semester. It was great. But anyway, bendy things, you just need a piece of string that you can then mark on and then straighten it out against the scale bar, right? What if you don't have a scale bar? What if you have a representative fraction and that's all you got? Or a verbal scale and that's all you got? Well, then you whip out your trusty ruler and you measure between thing A and thing B on the ruler, and then you got to do a little math, right? So the first thing we do is we've got our map distance, we've got our representative fraction, we want to get everybody in common units, right? So usually that's going to be inches or centimeters, right? If we can, we're going to simplify the numerator to 1. Right? We might wind up with a really huge denominator. Remember we looked earlier when we looked at large and small scale maps, some of those denominators are kind of ridiculous. So that's not entirely unsurprising. Right? So for example, we have here 1 inch equals 5 miles. This is my scale as noted on the map, my verbal scale, or my representative fraction, probably my verbal scale in this case because the units are different, right? So 1 inch equals 5 miles. map distance, ground distance. And then I'm going to convert to get everybody in the same units, right? So 1 mile equals 5,280 feet. Then I can cancel out those, right? And then I still have to go feet to inches, so I'm going to do one more conversion, 1 foot over 12 inches, right? And then I can cancel those out, and then I've got inches over inches, and so I can cancel out the inches. And then I get 1 to 316,800. And this is my representative fraction. So that's taking a verbal scale to a representative fraction. And then we know how many things we have on the map. So one thing on the map is 316,800 things on the face of the earth. And then we'll go through some examples here in the next video of how to get to the actual ground distance of the two things that you just measured. So this notation is one that I'm going to use all the way through the example slides. If you've done stoichiometry and you're more familiar with that notation style and you're comfortable with it, feel free to use it. It really doesn't matter what method you use as long as you get the correct result. Oops, those are slightly out of order, but anyway. So I get 1 over, right, multiply all the way across here, multiply all the way across here, and then we write it as an RF, okay? So I'm going to give you a few unit conversions to jot down and have handy for the next video where we're actually going to practice doing these scale conversions, okay? So 1 meter is equal to 100 centimeters, which is also equal to 1,000 millimeters, right? 1 kilometer equals 1,000 meters. Metric is so easy. It's just like, multiples of 10. It's great. Our weird English units, we have 1 foot equals 12 inches, and then 1 mile equals 5,280 feet. And then if you want to keep this number in your back pocket, it's super handy, 63,360 inches. And that's just 5,280 times 12 is how we get there, okay? And then switching between systems, 1 inch is 2.54 centimeters, 1 mile is 1.609 kilometers, okay? So jot those down, have those ready, and then in the next video, we're going to walk through some examples of calculating scale.